Hey guys, in this video I'm going to go over one of the examples in the textbook, example 7.4. Block being pulled on a rough surface. We have a block right here and it's being pulled by a force. It has some friction on it. It moves a distance delta x, and the book also gives the velocity in the figure, which isn't necessarily part of the free body diagram but is part of what's happening in the problem, which is the block is moving with some velocity vf. So I'm going to try to do this problem in a more systematic way than the textbook does. First thing I want to do is I want to define what my system is, because I want to use conservation of energy. So one thing I want to point out is there's actually two possibilities for what this system could be, and that's because we have a block and we have friction. So first we can think of the block as the system and friction as external to it and F as external to it. So then we would have the block as a non-isolated system with friction and the pushing force acting on it. Alternatively, we could think of the entire system as isolated, meaning the block and the surface, and then F being external to it. So there's various possibilities. What I'm going to do is I'm going to take the block and the surface as the system and have F is external, so this is a non-isolated system. So as a non-isolated system, it obeys equation 7.2 in the text, which we have right here. The delta K is the change in kinetic energy, delta U the change in potential, delta E internal the change in the internal energy. That's equal to the total work being done on the system. So equation 7.2 has some other terms, the heat, other kinds of energy transfer. There's nothing else in this problem. We have only friction and the pushing force, and so no other terms are going to show up in our expression. So let's start filling in some of these things. First thing to notice is that potential energy here, that goes to zero because there's no source of potential energy which could be changing. We have the gravitational energy, but that's going to stay constant because the thing is moving on a horizontal surface. We have no springs. We have no other sources of potential energy, so the change of potential energy is going to be zero. We can write down what the change in kinetic energy is going to be. Because we're being told in the problem that the block starts from rest, it's being pushed with some force, and we want to know what the final velocity is after 3 meters. So that means that the initial velocity is 0, the initial kinetic energy is 0, and so we have only this term in the kinetic energy. So we need to find the change in the internal energy and the work being done on the system. So this is where things can get a little confusing, because the internal energy depends on what you've defined as the internal to the system versus external to the system. I'm doing a non-isolated system where F is external and Fk is internal, so the system includes the surface. So that means that the change in the internal energy is due to the force of friction. And actually this is one thing that the text does pretty nicely. It says the change in the internal energy is the force of friction times the distance over which the block is moving. In our case, I'm going to change this into the symbols that we actually are using in this problem. So that's Fk times delta x, and this is equation 7.15 in the text where they define this. So what's left? Well, we have only the force that the block is being pushed with. That's the external force, and so that's the work being done on the block, which is F delta x. So we now look around and make sure that we have enough variables to solve the problem. We notice that we don't. We're looking for Vf, we have the mass, we have the force, we have delta x, but we don't actually have the force of kinetic friction. Well, that's just a Newton's second law problem. So here's Newton's second law in the y direction. Notice the book has a slightly different notation than I've been using in class. It writes N as the normal force. To me, this is Fn. Not too much confusion possible there. But you sum up these, you get 0, and so that tells you what the normal force is. And of course that tells you what the kinetic friction is, because the definition of kinetic friction is mu n, and so the kinetic friction is just mu mg. So in the next slide, I'm going to combine all these things together to find Vf, which is just going to take some algebra. So we started with this. Replacing all of our symbols, we get that. And now solving for Vf, we get the following. This is the same expression that the book gets, so we know that the answer is the same, 1.8 meters per second. And then the book makes the point that we've done this problem before, And with no friction, the final velocity here was 3.5 meters per second, and it's correspondingly less as we would expect. So the book goes on to ask a kind of interesting question, which is why I wanted to do this video. It asks that instead of pulling in the horizontal direction with the external force, you pull at some angle theta. And the question is, what angle will make the final velocity the biggest? Naturally, you would think that the angle would be 0 because you're pulling in the x direction as hard as possible. But of course, the more that you pull upwards, the less the normal force will be, and the smaller the force of friction will be. So the question is, what angle will actually maximize the velocity at the end? And notice that this would actually be quite a difficult problem if you're going to do Newton's laws, because you'd have to find the acceleration, you'd have to maximize the acceleration to find the velocity at the end. Doing energy conservation, this is going to be a significantly easier problem to solve. So we're going to start with our same energy conservation equation. I've left off the potential energy because I think we can all agree that the potential energy is not going to change in this situation. So here's that rewritten in terms of the variables in the problem. So notice this isn't going to be different than the original case because Fk is going to be different because now the normal force is going to be affected by a vertical component of the pulling force, and the parallel component of the force is not going to be as large because there's going to be some vertical component and some parallel component, so we need to take both of those into account. So here's our Newton's second law in the vertical direction, which gives us the normal force as the gravitational force minus F sine theta. That's minus the vertical component of the pulling force. The parallel component of the pulling force is going to be the x component of that force, which is F cosine theta. Putting all these expressions into the conservation of energy equation, we have the kinetic energy, then the frictional force, which is mu n coming from here, times delta x. This is the parallel component of the force, delta x, that's the work. So after some algebra, we can isolate Vf squared. A few things about this is Vf squared in terms of the angle. That's good because we want to find the angle which gives us the maximum Vf. And we have this exact same expression which we have nearly every time we do anything with friction and angles, which is cosine theta plus mu sine theta. So the book goes on, and actually what the book does, it differentiates the kinetic energy with respect to theta because it knows that if you maximize the kinetic energy, that's also maximizing Vf squared. I'm going to directly maximize Vf squared because I think that you guys, if you saw this on a homework or an exam, you would just go right to solving for Vf and trying to maximize that equation. That's actually a little bit harder than what the book does, so I thought that I'd show you what that looked like. Okay, so here's the Vf squared equation, so I'm first going to just take a square root of that. And now remember that what we're trying to do here is we're trying to maximize Vf. And when you want to maximize something and you have an actual equation for it, there's a calculus trick. You take the derivative of that thing with respect to the thing you want to maximize to. So I want to find which angle will give me the maximum final velocity, so I want to take that derivative, set that equal to 0, and then solve for that theta. So this is going to get a little bit nasty, but that's why I wanted to show you it, because these things actually do show up in introductory physics. So the first step in taking this derivative is to subtract 1 from the exponent, which is 1/2, so I subtracted that to 1/2, pulled out the 1/2 in front here. Now, of course, I also have to take the derivative of everything which is inside here, which is this. This is constant, then I take the derivative with respect to theta of the trig functions. Derivative of cosine is negative sine, derivative of sine is cosine, derivative of this is 0 because I'm taking the derivative with respect to theta and there's no theta in there. And I want to set this whole thing equal to 0, because remember, that's how we're going to maximize it. So this looks real nasty, but we want it to be equal to 0. So the question is, when is this thing going to be equal to 0? Well, we don't want this thing to vanish, because if this thing vanishes, that's on the bottom, that's going to blow up. So actually what we want to do is we want to make this thing in this parentheses equal to 0. So let me see if I can show you that schematically. So this is essentially what we have. We have the 1/2 out front, which I've just put there for clarity. I have A is this thing, and then I have B, which is this thing. So in sense, I can actually multiply times B and divide by 1/2 to just get that I want A to be 0. Well, if A is going to be 0 and A is this whole thing right here, then in order for A to be 0, this guy just has to be 0. And we get this nice little expression which the book also gets. And if you do a little bit of rearrangement, you get the tangent of theta is equal to mu. And you get something like theta is equal to 8 degrees. So 8 degrees is the right balance between decreasing the frictional force and decreasing how hard you pull, because as you increase the angle, there's going to be less frictional force, but you're actually going to be pulling a little bit less. So what you want to do is just raise the angle a little bit, and that will decrease the frictional force enough to maximize the velocity. That might be a little counterintuitive because you'd expect the angle to be 0, but we can show mathematically that it's 8 degrees. So this is not something which I would ask you to do on an exam. This is probably not even something I would ask you to do on homework. This is a tough problem, but I wanted you to see it because this really is a technique which should be available to you because you know about calculus. But these things actually do show up in introductory physics, and once you have the material we've been doing in class, you can do things like this. So I thought you should see it. Okay guys, thank you very much for watching the video, and I will see you in class.